Hi, now I am going to discuss numerical methods. Generally, we can see two types of equations. One is algebraic equation and the second one is transcendental equation. Algebraic equation means it is a normal polynomial. Suppose you can see here some x cube minus 3x square plus 4 equal to 0. It is algebraic equation. Means we are writing a polynomial in x. It is a simple polynomial. Transcendental equation. Suppose one equation contains trigonometric functions or logarithmic functions or exponential functions, etc. In that case, the equation is called transcendental equation. Suppose you can see here e power x plus x power 4 equal to 0 or sin x plus x cos x equal to 0. Log of e power x square minus tan x equal to 0. These are the transcendental equations. If we find any special function in the equation, generally it is called transcendental equation. Suppose the function is algebraic or transcendental, then what is the meaning of the root of the function? See, the root of the function or the root of the equation means the value of x which satisfies the given equation. For example, the equation is x minus 2 equal to 0. See here, x equal to 2 is a root because x equal to 2, if you put here x equal to 2, 2 minus 2, left hand side is 0 and right hand side is also 0. So x equal to 2 satisfies this equation, means x equal to 2 is a root of that equation. See, the process of finding the roots of given equation is known as solution of that equation. I will take another example here. Suppose the equation is x square minus 9 equal to 0. So what are the roots here? X equal to 3 comma x equal to minus 3. 3 comma minus 3 are the roots. If you put x equal to 3 or x equal to minus 3, you will get left hand side equal to right hand side. So 3 comma minus 3 both are the roots of the equation. And we can also say x equal to 3 and minus 3 are the solutions of the equation. You can say roots or the solutions of the equation. You have to observe one point here. X equal to 3 is a root. So x equal to 3 is a root means here x minus 3 is a one factor of that equation, that polynomial x square minus 9. Similarly, x minus of minus 3 is also one factor of this polynomial. You can see we can write this x square minus 9 as x minus 3 into x plus 3. So x minus 3 and x plus 3 are the factors of the polynomial x square minus 9. What is the geometrical interpretation of the root? See, if a is a root of the equation f of x equal to 0, then the graph of the function y equal to f of x crosses the x-axis at x equal to a. Now you can see one important property. Suppose the function has different signs at x equal to a and at x equal to b. You can see the graph. We are taking one function y equal to f of x. This function is negative at x equal to a and positive at x equal to b. Then we can find a number between a and b. See, you can see one number alpha between a and b. At this number, the functional value is 0. Means here f of alpha equal to 0. This is one most important property of the function. Suppose a function has different signs at two numbers, then there exists a value between the two numbers. At that value, the function is 0. Now we have a question: how to find the root of the equation? See, if it is one simple algebraic equation, easily we can find the root of that equation. Suppose x plus 1 equal to 0. What is the root of the equation? Simply we can write here x equal to minus 1 is a root. Without any calculations, directly we can identify the root here. Another example, if the equation is suppose x square minus 16 equal to 0. What is the root of this equation? It is very simple thing. We can factorize this polynomial. So what are the factors here? X minus 4 into x plus 4 equal to 0. From this we can write down x minus 4 equal to 0 or x plus 4 equal to 0. That implies x equal to 4 comma x equal to minus 4 are the roots. If it is one simple algebraic function, easily we can find the roots of that equation. Suppose the function is transcendental or algebraic function with higher degrees. In that case, calculation of root is little difficult. Then how we can find the root of that equation? In this case, we can use numerical methods. By using numerical methods, we can find the root of any type of equation. And the most important thing here, numerical method gives only approximate value of the root, not exact roots. One basic method to find the root of the equation, that is bisection method. By using bisection method, we can find the root of any equation. Already we know one property of the function. Suppose f of x is continuous between a and b and f has different signs at a and b. Then there exists a root between a and b. By using this, we can find the root of any equation in bisection method. Now we will see what is the procedure in bisection method. Let f of x be a continuous function in the interval a comma b and the function has different signs at a and b. Then there exists a root of the function between a and b. Suppose the function has positive value or negative value at a. So at this point the function is negative. F of a is negative. And at b the function is positive. Okay, the function is negative at a and positive at b, means the function has opposite signs at a and b. Already we know. Then there exists a root of the function between a and b. Now to identify the root, we are taking the midpoint of this interval. So the midpoint is a plus b by 2. We can take that one as c. Now we have to find the functional value at c. Suppose at c the function is positive, then the root lies in between a and c now, because already we know the property. If function has different signs at two different points, then the root of the function lies between the 2 points. Suppose here if the function is positive at c, already the function is negative at a, so the root lies in between a and c. Or there is another possibility. Suppose at c the function is negative. Suppose at c the function is negative and at b the function is positive, means at c and b the function has different signs. So the root of the function lies between c and b. Then we consider the midpoint of c and b. What is the midpoint of c and b? C plus b by 2. We can take this one as e. Now we find the functional value at e. Suppose at e the function is negative. Then you can observe here at e the function is negative and at b the function is positive. So the function has different signs at e and b. So the root lies in between e and b. Again we can take the midpoint of e and b. So the midpoint is e plus b by 2. I'm taking the midpoint as suppose some m. We calculate the functional value at m. Suppose the functional value is positive at m. Then the root lies in between e and m because the function has opposite signs at e and m. See, we have to continue this process. It is the iteration process. In every step, we are moving to very close to the root. After few steps, we can identify the better approximation of the root in this method. Now you can see the graphical representation of the bisection method. See, the function y equal to f of x. See, this function has root at this point. This is the root of this function. And the function has opposite signs at a and b. At a, the function is negative, and at b, the function is positive. See, we have to identify this value of the root. First, the first approximation, you can see here. Suppose x1 is the first approximation, that is the midpoint of AB, and at x1, the function is positive. Look at that. So the root lies in between a and x1. Next, we are taking the midpoint of a and x1. Suppose the midpoint is x2. At x2, you can see the value of the function, it is negative. Now, the root of the function lies in between x2 and x1. So we have to take the midpoint of x2 and x1, then midpoint is x3. At x3, again the function is positive. So the root lies in between x2 and x3. So we have to take the midpoint of x2 and x3. Suppose the midpoint is x4 and at the x4 the root is, the value of the function is negative. So at x4 the function is negative and at x3 the function is positive. So the root lies in between x4 and x3. Now we can take the midpoint of x4 and x3. Suppose it is x5. We take the, we write the value of the function at x5. Suppose it is positive. At x5 the function is positive, at x4 the function is negative. So the root lies in between x4 and x5. In next step again we find the midpoint of x4 and x5. See, we have to continue this process. After few iterations, we can reach the exact position of the root. Now we will discuss one example how to find the root of the given equation. In this example, the equation is x cube minus 4x minus 9 equal to 0. First, I am taking the polynomial as f of x. So let f of x equals to x cube minus 4x minus 9. Already we know the concept in bisection method. We have to identify the interval. In that interval, the root of the function exists. So how do you identify the interval? See, at starting point and at ending point of the interval, the function should have opposite signs. To identify the interval, it is very simple thing. You have to substitute the numbers in this function and you can verify where you are getting positive and negative. Suppose if I start with 0, if x equal to 0, what is the functional value here? F of 0 equal to -9, negative. Next, I can take f x equal to 1. So f of 1 equals to 1 minus 4 minus 9. So the value is -12. It is negative. If x equal to 2, f of 2 equals to 8 minus 8 minus 9. Again, it is negative. See, you have to continue this process until you have to get opposite signs for two consecutive numbers. Next, if x equal to 3, f of 3 equals to 27 minus 12 minus 9. So the value is here 6, positive. Now you can observe at x equal to 2, the function is negative, and at x equal to 3, the function is positive. So the root of the function lies in between 2 and 3. By using bisection method, we have to identify the approximate value of the root in between 2 and 3. Always we have to read the question properly. Suppose if you find a equation in the question like this, x cube minus 4x equal to 9. This is the given equation. Look, if you consider the function as f of x equal to x cube minus 4x, this is wrong. Look, first from the given equation, you can write x cube minus 4x and minus 9 equal to 0. Always you have to keep 0 on right hand side. Then you have to consider f of x. So you can write here f of x equals to x cube minus 4x minus 9. So this is correct one. So you have to remember this. First you have to equate that expression to 0. Then you have to write left hand side one, left hand side polynomial or left hand side function as f of x. Already we have verified that the function is negative at 2 and positive at 3. So the root of the function lies in between 2 and 3. For my convenience, I am taking the number line here. At 2, it is negative. At 3, it is positive. The root lies in between 2 and 3. So the first approximation is the first approximation of the root is x1, that is the midpoint of 2 and 3. So we can write x1 equals to 2 plus 3 by 2. The value is 2.5. In next step, we have to find the functional value at 2.5. See, what is the functional value at 2.5? F of x1 equals to here minus of 3.375. So it is negative. Already we know At 2 it is negative, and at 3 it is positive. So at x1 the function is negative. It is a midpoint, but for my convenience I will write here. Actually we have to write exactly in the middle, but only for convenience I am writing here. So at x1 the function is negative. Now the root lies in between x1 and 3. So what is the next approximation of the root? That is the midpoint of x1 and 3. See, we are finding the midpoint of x1 and 3 here. What is the midpoint of x1 and 3? It is 2.75. That is the next approximation of the root. Now we find the functional value at x2. You can see the functional value at x2, 0.7969. It is positive. So at x2 the function is positive. Now I will mark x2 on the number line. Actually it is the midpoint of x1 and x3, but I don't want to write in the middle. Only for my convenience I can mark that x2 here. At x2 the function is positive. You can observe at x1 the function is negative, and at x2 the function is positive. So the root lies in between x1 and x2. The next approximation of the root is x3. It is the midpoint of x1 and x2. You can see we are calculating the midpoint of x1 and x2. That is the next approximation of the root. That is x3, 2.625. In next step, we find the functional value at x3. You can see what is the functional value at x3 here. The functional value at x3 is minus 1.4121. It is a negative value. Now I will mark this one on number line. At x3 the function is negative, so I can mark that x3 here. Actually x3 is the midpoint of x1 and x2. Only for my convenience I can mark here x3, and the function is negative at x3. The next root of the function lies in between x3 and x2. So we can write the next approximation of the root, that is x4. It is the midpoint of x2 and x3. Look at the value. The value is 2.6875. In next step, we find the functional value at x4. We repeat this process until we get the better approximation of the root. If you observe, I'm calculating up to x12 in this problem. You can raise simple question where we will stop this process, because it is an infinite process. After x12 you can calculate x13, x14, x15. It is a continuous process. So how can we stop at x12? In given question, maximum we can find stopping criteria of the method. You may find like this: stop after 7th iteration, or stop after 4th iteration, find 10th iteration, then you can stop at 10th iteration. Or you may find like this: you have to find accuracy up to 3 decimal places, or accuracy up to 4 decimal places. What does it mean? Accuracy at 3 decimal places means in 2 consecutive values, after point 3 decimal places must be same. Suppose if you see here in x5 and x6, you can see 2.71, 2.70. This is same up to 1 decimal place. If you compare x6 and x7, 2.70, 2.71, again it is same up to first decimal place. Now we have to compare x7 and x8. x7 2.71 and it is 2.70. It is same up to first decimal place only. We have to compare x8 and x9. See, x8 is 2.707, x9 2.705. See, these values are same up to second decimal place. We need accuracy up to fourth decimal places. So we have to continue. In x10, we are getting 2.706. Again, x9 and x10 are same up to second decimal place only. Then we have to compare x10 and x11. These are same up to three decimal places. So finally, x11 and x12 are same up to three decimal places. So we are stopping the process at x12. Means we are expecting the accuracy up to three decimal places. So what is the approximate value of the root? That is 2.7064. This is the final answer. So this is the root of the given equation. I'm taking another example. Sometimes you may find question like this. Using bisection method, find the negative root of the equation. You can see here, negative root of the equation. In this case, already we know to identify the root of the function, first we need the interval. At the end point of the intervals, the function should have opposite signs. So here we need negative roots. So we have to consider interval with negative numbers. For that, we can write here. See, we have to observe where we are getting negative roots. I will start with -1. Suppose x equals to -1. F of -1 equals to, what is the value here? -1 plus 4 plus 9. The value is 12. It is positive. Next, x equal to -2. So f of -2 equals to -8 plus 8 plus 9. It is 9. Again, it is positive. Now I can take x equal to -3. So f of -3 equals to -27 plus 12 plus 9. This equals to 6. I think it is -6. So negative. See, at -2 and at -3, the function has opposite signs. So on number line, I can take these two numbers. At -2, it is positive. At -3, it is negative. The next root of the function lies in between -2 and -3. Now we can take the midpoint of -2 and -3. That is the first approximation of the root of the function. By using the procedure what we have discussed in the previous example, you can find the better approximation of the negative root of this equation. The answer for this problem is -2.7064. You can try this one. Here we have one more example. What is the given equation here? sin x equal to 1 by x. Already we know right hand side we need only 0. So we have to bring this complete 1 by x to on left hand side. Simply I can write x sin x equals to 1. So finally x sin x minus 1 equal to 0. Now what is my function here? F of x equal to x sin x minus 1. This is the function. And one more thing, generally here, see this is transcendental equation because you can find sin x. We write x here either in degrees or radians. But to solve this problem, always we write x in radians because here x means this is a normal number, but here x means here it is an angle. So only here you can write degrees or radians. So you can't write degrees here. That's why always we have to use x in radians. You can also see in the given question, already given the interval x equal to 1 and x equal to 1.5. These values are considered in radians. Now you can see the procedure. Already we discussed how to find the approximate value of the root for the given equation. See, given interval is 1 comma 1.5. So first we have to see the nature of the function at 1 and 1.5. At 1 it is in negative, at 1.5 it is positive. So you can mark 1 here, it is negative, and 1.5 it is positive. The next the next approximation of the root that lies in between 1 and 1.5, it is the midpoint of 1 and 1.5. See, we are calculating the next approximation. It is the midpoint of 1 and 1.5. Okay. In next step, we see the nature of the function at x1. The nature of the function at x1 is positive. Okay. So I can mark x1 here. The next approximation of the root lies in between 1 and x1. So the next approximation is the midpoint of 1 and x1. So this is the next approximation of the root, that is 1.125. In next step, we find the nature of function at 1.125. If it is negative, I can mark here. If it is positive, I can mark here. Okay, how to continue this process? And you have to observe one thing. In my calculation, see, you can observe here, I have written this value in degrees. Actually, it is not compulsory. Simply, you can write here 1.25. Suppose if you want to write angle in degrees, first you have to convert that 1.25 radians in degrees. Then you can write that 1.25 radians is exactly equals to 71.625 degrees. So instead of 1.25, you can use in degrees. Actually, it is not compulsory. Here also, see, x sin x, here x equal to 1. So 1 into sin 1. If you want, you can also write this one as 1 into sin 1. You have written here 1 radian equals to 57.3 degrees. So you can write 57.3 degrees minus 1. There is no issue. But don't use in degrees. Always you have to write in radians only. Don't confuse. In your calci, you have to keep your calci in radians and calculate it. If you continue the iteration process, you can see here at x3 the function is negative. At x2 the function is positive. So the next root lies in between x3 and x2. After some iterations, already it is mentioned that we have to find 7 iterations. So after 7th iteration, you can stop the procedure. See, at 7th iteration, the approximate value of the root is 1.11328. This is the final answer because in question already it is mentioned that find up to 7 iterations. So after 7th iteration, you can stop the procedure and you can take the 7th iteration value as the final answer. So the root, not exact root, the approximate value of the root of given equation is 1.11328. Now we will discuss Newton-Raphson method to find the approximate value of the root of the equation. In this method, you can see here, we are taking x naught is an approximate root of the equation f of x equal to 0 and x1 is the exact root of the equation. Then we can write down, because x1 is exact root. So if you put x1 in the equation, we get 0. So we can write down here f of x1 is 0. But x1 is x naught plus h. If you replace x1 with x naught plus h, then f of x naught plus h equal to 0. By using Taylor series expansion, we can write this one as f of x naught plus h into f dash of x naught plus h by 2 factor into f double dash of x naught plus so on equals to 0. From this equation, we can write h equals to minus f of x naught by f dash of x naught. See, we have to ignore the higher order derivatives. Means we are not considering this f double dash, f triple dash, so on. Suppose if you ignore the higher order derivatives, what is the result here? F of x naught plus h into f dash of x naught equal to 0. We are not taking second, third, fourth order derivatives. So from this h equals to minus f of x naught by f dash of x naught. We substitute this h value here. Then what is x1? Now we can see after substituting that h value, we can see x1 equal to x naught minus f of x naught by f dash of x naught. See, x naught is the initial approximation. By using x naught, we are finding the better approximation, that is x1. Similarly, by using x1, we can find the next approximation, that is x2. In the same way, we can find x2 by using x1. This is the next better approximation. Again, by using x2, we can find x3. In general, we can write down xn plus 1 equals to xn minus f of xn by f dash of xn. This is Newton's Raphson formula. Now we will see the geometrical interpretation of the Newton-Raphson method. Suppose x1 is the first approximation of the root of the function y equal to f of x. You can see this is the graph for y equal to f of x, and x1 is the first approximation of the root. At x1 we can see, at x1 we can draw the tangent. This tangent intersects x-axis at x2. Now we can consider this x2 is the second approximation for the root of the function. At x2, again we can draw one tangent to the curve. This tangent intersects x-axis at x3. Now the x3 is the next approximation of the root. At x3, we can draw another tangent to the curve. This tangent intersects the x-axis at x4. If we continue this process, we can reach the exact root after few iterations. So in every step, we are constructing one new tangent. That new tangent generates the next approximation of the root. This is the geometrical interpretation of the Newton-Raphson method. Now we solve one problem by using Newton-Raphson method. To start the procedure, first we need initial approximation. We have to follow the same procedure what we are using for bisection method. See, what is the given equation here? X power 4 minus x equal to 10. Right hand side is not 0. So we can write this one as x power 4 minus x minus 10 equal to 0. Now the function is f of x equal to x power 4 minus x minus 10. In Newton-Raphson method, we need derivative of the function. So f dash of x equal to 4x cube minus 1. See, first we have to identify the interval where the root exists. To identify the interval, we have to find the functional value at different numbers. I will start with 0. If x equal to 0, what is f of 0? It is minus 10, negative. If x equals to 1, what is f of 1? 1 minus 1 minus 10. Again it is minus 10, negative. If x equals to 2, f of 2. 16 minus 2 minus 10. It is 4, positive. See, at x equal to 1, the function is negative. At x equal to 2, the function is positive. So the root of the equation lies in between 1 and 2. We have to consider the initial approximation of the root. To consider the initial approximation, we can consider x naught equals to 1 or x naught equals to 2, or you can take x naught equal to midpoint of 1 and 2, 1.5, or you can take any number between 1 and 2. You can also take some 1.3 or 1.4. So you can consider initial value in the from the interval 1 comma 2. That is your choice. In general, we can start with 1.5, or you can also start with 1. See, I'm taking the initial value as 2. So the initial approximation of the root is 2 because the interval is 1 comma 2. From 1 to 2, you can choose any number as initial value. By using x naught, we have to find the next approximation, that is x1. Now I need Newton-Raphson formula. See, this is the Newton-Raphson formula to find the next approximation. To find x1, I have to put here n equal to 0. If I put here n equal to 0, I can write x1 equal to x naught minus f of x naught by f dash of x naught. Our x naught is 2. So I have to put here x naught equal to 2. Then I will get here 2 minus f of 2 by f dash of 2. The functional value at 2 and the derivative value at 2. So the value is 1.871. This is x1. Directly by using this x1 value, we can find x2. To get x2 in this formula, in Newton-Raphson formula, I have to put n equals to 1. We are substituting here n equals to 1. So x2 equal to x1 minus f of x1 by f dash of x1. We have to put x1. What is our x1? It is 1.871. See, the result is 1.856. That is x2. Next, for next approximation, we can use x2. See, we are calculating next approximation x3 by using x2. So the next approximation is 1.856. Actually, this is equal 1.856. If you observe the second approximation, that is also 1.856. Third approximation is also 1.856. Two consecutive values are same up to third decimal place. So I can stop this iteration process here and I can consider the approximate value of the root of given equation is 1.856. So my answer is 1.856. This is the final answer. Now we can see another example. What is the equation here? 3x equal to cos x plus 1. So I can write this one as 3x minus cos x minus 1 equals to 0. So f of x equals to 3x minus cos x minus 1. Now we need the interval. The interval contains the root of this function. To identify the interval, I can put here x equal to 0, x equal to 1, x equal to 2, x equal to 3, so on. For two consecutive substitutions, I have to get opposite signs of the function. See, already we discussed, it is a transcendental equation. You can find trigonometric terms. See, whenever you find the trigonometric terms in the equation, always you have to write x in radians. Don't use degrees. Now you can see here, at x equal to 0, the function is negative. At x equal to 0, the functional value is negative. At x equal to 1, the functional value is positive. Means the root of the function lies in between the 0 and 1. Now we can take the initial approximation of the root. See, that is x naught. See, you can take initial approximation of the root any value from 0 to 1. So I am taking x naught equal to 0.6. Next, you have to write Newton-Raphson formula here. See, this is the formula. See, in this formula, we are substituting f and f dash. See, I need here f dash of the function. So, what is f dash? 3 plus sine x. I have to substitute f of x and f dash of x in this formula. Now, this is the formula xn plus 1 equals to. For first approximation, I have to put here n equals to 1. If I substitute n equals to 1, I can find x1. Not n equal to 1, I have to put n equal to 0. If I put n equal to 0, I get x1 equals to x naught sine x naught plus cos x naught plus 1 by 3 plus sine x naught. Already we have x naught value 0.6. If we substitute x naught here, that gives the next approximation x1. See the value of x1 here. It is 0.6071. Now by using this x1, we can find the next approximation, that is x2. See, from formula, I'm writing first x2. Then we have to put here x1 value. After substitution of x1, we can find x2, that is 0.6071. So finally, you can observe that x1 and x2 both are equal, 0.6071. So x1 and x2, two consecutive values are same up to fourth decimal place. So we can stop this iteration process here. And the final answer is 0.6071. So the better approximation of the root of given equation is 0.6071. Now we will discuss numerical integration of the function. What is meant by numerical integration and why do we need this? See, in few cases, our analytical method is not applicable to find the integration of given function. In that case, we can go for numerical methods. Suppose the integration of the function is more difficult, or the function is not integrable, or we don't know what is the explicit form of the function, means we have only functional values. We have a table with functional values. We don't know what is the explicit form. In that case, our analytical method will not work. Then we use numerical integration. So numerical integration means the process of evaluating a definite integral from the set of tabulated values. Means tabulated values means your functional values. Okay, this process is called numerical integration. Suppose if we apply this process to single variable function, then it is known as quadrature. Already we know numerical method always gives the approximate values, not exact answers. Now we discuss Newton-Cotes quadrature formula. See, we have to integrate the function y equal to f of x between a comma b. See, we know only functional values at x equal to x naught, x1, x2, so on, xn. The functional values are y naught, y1, y2, so on, yn. Now we divide this a to b interval. Look at this into subintervals. We are dividing that a to b interval into subintervals. We are taking that a as x naught and next value x1, that is x naught plus h, x2 x naught plus 2h, or x1 plus h. Here h is the common difference between x values. You can also see the graph. This is a and this is b. We are dividing this a to b into subintervals. Next, we need this integration value. Now we are writing that integration as, look at this, x naught to x naught n plus nh. Our initial value is denoted by x naught and the final value is x naught plus nh. Means we are dividing that a to b interval into n subintervals with common difference h. We are substituting here x equal to x naught plus rh. Now you can see the integration h into integral of 0 to n f of x naught plus rh dr. We are using Newton's forward interpolation. See, we are approximating this function by using Newton's forward interpolation. This is Newton's forward interpolation formula. Now we have to integrate each and every term in this formula with respect to r. You can see the result here. After integration, see, this is the final expression. This is known as Newton-Cotes quadrature formula. By using this formula, we can integrate the function by using given limits. In this formula, we can use n equal to 1, 2, 3, so on. N means number of subintervals. See, in Newton-Cotes formula, we are using n equals to 1. If we use n equal to 1, means we are using only one subinterval. Means first we are taking this subinterval. It is x naught to x naught plus h. Only in this interval we are calculating the integration value. You can see here. We are taking only one subinterval, means x naught to x naught plus h. So this is the integration value. After that, we can take the second subinterval. What is the second subinterval? X naught plus h to x naught plus 2h. We can see. In every time, we use only one subinterval and we write the integration value. We have to continue this process. Finally, this is x naught plus n minus 1 into h to x naught plus nh. You can see here. For every subinterval, we are calculating integration separately. Okay. See, means this part of curve is approximated by straight line. See, means you are getting your straight lines. See, every strip is one trapezoid area. That's why this rule is called trapezoidal rule. After getting all integral values, we add all integration values. See, by adding these n integrals, you will find this expression. So what is this? This is integral of a to b f of x dx value. Here a means x naught, b means x naught plus nh. So this formula is called trapezium rule or trapezoidal rule. Because in every interval we can see one trapezium. That's why this is called trapezoidal rule. Once again you can see why we are using that previous formula as trapezoidal rule. What we are doing there, in every subinterval, means in every interval, we are finding integration separately. Finally, we are adding all the integral values. That gives the total integration value of the function from a to b. See, in every subintervals, you will find one trapezium. I think you know the meaning of the trapezium. You can see here. What is the meaning of the trapezium here? You can observe I have written trapezium means you will find one pair of parallel lines. Okay, you can see these two opposite sides are parallel. Here, these two opposite sides are parallel. These two opposite sides are parallel. This is the only condition for the trapezium. If you observe every subintervals, you can see these two lines are parallel. So this is one trapezium. Now, what is the area of trapezoid or trapezium? Of a plus b into h. A means the length of the a comma b means here length of the parallel sides. H means the perpendicular distance between two parallel sides. So of a plus b into h. Here we can write the area of every trapezium by adding all these areas finally we can find the area bounded by that curve. Means area means the integration of the function. Here area means, what is the meaning of area? The integration of the function from a to b. In Newton Cotes formula, if we use n equal to 1, we are getting trapezoidal rule. Now, if we put n equal to 2 in Newton Cotes formula, we can find Simpson one-third rule. See, using n equal to 2 means we are integrating the function on two subintervals. Every time we have to consider two subintervals and we find the integration. You can see here, first we are taking two subintervals, x0 comma x1, then x1 comma x2. First integration on these two subintervals means here x0 to x0 plus 2h. x2 means I can write this one as x0 plus 2h. You can see the first integration. Similarly, this is the second integration. If we continue this, this is the final integration. Every time we use two subintervals for integration. So by adding all these integral values, we can find the total integration of the function from a to b. This one is called Simpson one-third rule. Now we will see what is the geometrical meaning. See, every time we are using two subintervals. See, suppose if we take the first two subintervals, means we are approximating this part of the curve by using parabola. See, if you have only one point, one subinterval, means you will get the straight line. If you use two subintervals, means if you use 2 points, x0 comma x1 and x1 to x2, then you can construct the parabola. Means we are approximating this curve with parabola. Now I am separating two subintervals from the above curve. See, this is, we are separating two subintervals. I'm approximating the virginal curve with parabola. The equation of the parabola is here, y equal to ax square plus bx plus c. Instead of the virginal curve, I can integrate this parabola equation. Means I'm approximating the integration of the virginal curve with the integration of the parabola. From minus h to h, I'm taking the interval minus h to h. See, what is the integration? Look at this. We are integrating the parabola. Instead of virginal curve, we are integrating the parabola. See, after integration, this is the result. But I have to write this result with functional values. To write this result in functional values, see, at every point, this is this one, this is this point, and this is this one. At 3 points, I'm substituting these 3 points in the function. After solving, I will get this. So finally, I will substitute this c and 2ah square in my integral values. See, this is the final integral value. H by 3 y0 plus 4 y1 plus y2. This is the integral value of one strip in two subintervals. Similarly, we can find the integration value for every two subintervals. Finally, we have to add all these integral values. See, when you add all these integral values, this is your final answer. So, integral of a to b f of x dx. What we are doing, instead of the left hand side direct integration, for every two subintervals, we are constructing one parabola. means that part of the curve we are approximating with parabola and we are integrating that parabola equation. Finally, we are adding all those integral values. So finally, we can find this. This is called Simpson one-third rule. Now, Simpson 3/8 rule. In Newton Cotes formula, if we use n equal to 3, n equal to 3 means every time we have to use 3 subintervals. So we have to integrate the function in 3 subintervals. In Simpson one-third, we are using only 2 subintervals. Now we are using 3 subintervals. See, this is the integral value. In next step, we can consider next 3 subintervals. Again, we have to integrate in next 3 subintervals. If you continue in this way, you will find all the integral values. By adding all these integral values, you will find the integration of the function from a to b. This is the final value. This is called Simpson 3/8 rule. Now you can see the 3 rules: trapezoidal rule, Simpson one-third rule, and Simpson 3/8 rule. You have to observe one thing. For trapezoidal rule, there is no restriction on subintervals. You can divide that given in integral limits into n number of subintervals. There is no restriction on n. But for Simpson one-third rule, see, every time we are using 2 subintervals. So the number of subinterval must be even number. In Simpson 3/8 rule, every time we are using 3 subintervals. So the number of subintervals must be multiple of 3. Here we have one example. By using trapezoidal, Simpson one-third and Simpson 3/8 rule, we are solving one integration. You have to observe that. What are the integral limits? Here, integral limits are x equal to 0 to x equal to 6. Next, what is the integrand? The function 1 by 1 plus x square. By using trapezoidal, Simpson one-third, Simpson 3/8, we have to find the integration of this function with integral limits 0 to 6. See, we have to divide this interval 0 to 6 into subintervals. Already we discussed, for trapezoidal rule, there is no restriction for the number of subintervals. For Simpson one-third rule, number of subintervals must be even number. Simpson 3/8 rule, the number of subintervals must be multiple of 3. I will choose one common value. I am choosing here n equal to 6 means number of subintervals equal to 6. So this is applicable for 3 rules. Trapezoidal rule, there is no restriction, so n equal to 6 is acceptable. For Simpson one-third, n must be even, 6 is even number. Simpson 3/8, n must be multiple of 3. Yes, 6 is multiple of 3. So this is acceptable for the 3 rules. See, what is the first step? You have to construct the table with functional values. To construct the table, first you have to write x values. See, what is the starting value of x? It is 0, your lower limit of the integration. Next value, starting value is x naught. Next value is x1, means it is x naught plus h. The next value is x2, means x1 plus h. Next one is x3, x2 plus h. Next one x4, x3 plus h. So what is h here? H means, suppose your integral limits are a to b. So b minus a by n, number of subintervals. So here b means 6, a means 0, number of subintervals is also 6. So h is 1. Your x naught means lower limit of the integration 0, x1, 0 plus 1, it is 1. x2, x1 plus h2, x3, x2 plus h, it is 3. Now look at this first row of the table, x1, x2, x3, x4, x5, x6. Substitute x values in the function, you will get y0, y1, y2, y3, y4, y5, y6. This is the first step. You have to find the functional values at different x values and put in a table. Next, write the formula for every rule. See, for trapezoidal rule, this is the formula. You can substitute all these values from the table. Already we know h value is 1. See, in this formula, we are substituting the values on right hand side. Y0 plus yn, y6, lost value, plus 2 into sum of the remaining y values. This is from trapezoidal rule. Next, by Simpson one-third rule. See, it is easy to remember h by 3 of first and last plus 4 into odd values plus 2 into even values. Look at this. So after substitution, this is the answer. Next to Simpson 3h. This is Simpson 3h. After substitution of all values, this is the final answer. You can also observe one thing. This is the exact value of the integration. Already we know integration of 1 by 1 plus x squared tan inverse x. So substitution of upper limit and lower limit, tan inverse 6 minus tan inverse 0. Tan inverse 0 is 0. So the answer is tan inverse 6. Tan inverse 6 value, this one, 1.4056. Now you can see by using trapezoidal, Simpson one-third and Simpson 3/8 rules, we are getting approximate values, not exact value. This is exact value. Our direct integration gives the exact value. The difference between approximate and exact, that is called error. See, in every method, you can see what is the error in trapezoidal, Simpson and Simpson one-third and Simpson 3/8. In this next example, you can see one simple application. The velocity of a moped is given. Now we have to find the distance covered by the moped in 20 minutes. See, we have to find the distance. Velocity is given. See, we don't know what is the explicit form of the function. We have only tabulated values. So by using numerical integration, we can easily calculate this. Once you can see, already we know the relation between displacement and velocity. The rate of change in displacement is velocity. So ds by dt equals to v. Integrating on both sides, you can see s equal to integral of v dt. Now the integral limits are 0 to 20. Don't confuse. Your time starts from 2 in the table, 2 to 20, but in integration I have written 0 to 20. You have to observe the statement that moped starts from rest. So you have to consider time from 0 to 20. At 0, the velocity is also 0. Now you can see I have written here velocity is 0 at 0. Next, at 2, velocity is 10. At 4, the velocity is 18. At 6, the velocity is 25. See, in Simpson one-third rule, it is very simple. Already we discussed h by 3 of first and last values plus 4 into odd plus 2 into even. So first we are adding odd values, then we are adding even values separately, and we are substituting in the formula. First and last, 4 into odd, sum of odd plus 2 into sum of even. See, this is the final answer. So in 20 minutes, the moped covers 309.33 kilometers. This is one simple application of numerical integration. You can see one more application in this numerical integration. If you observe the tabulated data, velocity is given and displacement is also given. Now we have to find the time. We have to estimate the time. It is very simple. Look, already we know the relation between velocity and displacement. ds by dt equals to v. See, don't take integration directly, because if you take the integration, you will get s equal to integral of v dt. See, our question is not for s. We have to find time. To find the time, you have to take the reciprocal on both sides. Look at this. Now you can integrate on both sides. If you integrate on both sides, you will get here t equal to integral of 1 by v ds. Okay. With the help of this integration, you can estimate the time. Again, you can use the Simpson one-third rule. With the help of Simpson one-third rule, you can find time. But very carefully here, we are not using v, we are using 1 by v. Okay, it is denoted by y. See, the table consists only v values. Now we need 1 by v. So first you have to write 1 by v values. Then you have to put all these values in the formula. So you will get the final answer. Now we can discuss one more example in this numerical integration. You can see the data. A revolution of a solid rotating about x-axis. The area between x-axis and the lines x equal to 0 and 1. And the curve to the points with the following coordinates. See, given x values and the corresponding area y values. Now we have to estimate the volume of the solid. With the revolution of the area about x-axis forms a solid. Now we have to estimate the volume of that solid. Again, I can use numerical integration. See, the volume of the solid generated by revolution of area about the axis, x-axis. This is the formula. Here x limits are 0 to 1, so integral 0 to 1 pi y square dx. See, you need your y square, not y values. So we have to square these y values at the time of substitution in the formula. You can use Simpson one-third rule formula and substitute tabular values here. So you will find the volume of the solid generated with the revolution.